Hi everyone. Thank you for having us here today. In Albert Einstein's words, imagination, he felt, was more important than knowledge because knowledge is limited, whereas imagination embraces the entire world, leading to evolution and stimulating progress. Technology in our workplace is moving at such a rapid rate that what we could do in 5 years yesterday, we can do in 5 months now, and maybe even 5 minutes next year. But whilst this technology is completely reshaping our workplace and to some degree even disrupting it quite dramatically, the concept of precision medicine is an interface that if we engage with it and harness it, it allows us to really be very creative with it. So over the last few years, we've had a lot of exposure to 3D printing at this symposium, and over there in the stage, we've got a 3D printer printing away, and now it's a desktop version. But the talk today is about stretching the imagination to explore new frontiers of that technology called bioprinting. Why are we talking about bioprinting? Well, RPA is about to become the first hospital in New South Wales to have its own bioprinting laboratory. And of course, that's a reason to celebrate, but we also want to spread that knowledge, to disseminate it, so it empowers each and every one of you to engage your own imagination and think about applications in your own individual specialties. To help me discuss this in further detail, please welcome to the stage Professor Gordon Wallace. Gordon is a professor at Wollongong, and not only has he been awarded an Order of Australia, he's also was awarded the 2017 New South Wales Scientist of the Year. In fact, Gordon's won so many awards, it's very difficult to think what he could be eligible for winning in 2018, except maybe the Toon Irish Dancing Championships or something.
I'm very good at Irish dancing.
Gordon, can you tell us a little bit about 3D printing?
Sure, so 3D printing has really turned the way we make things literally on its head. We used to think about making things by chiseling out shapes from different materials and combining those materials, and that is quite limited. Whereas we turn to 3D printing, we create structures layer by layer. We build something from the ground up. It means it's very versatile. We can introduce different types of materials during the printing process, so we can create quite complex structures. It also means that we can do it because these are simple instruments, as you can see, simple devices. And we can bring that ability to manufacture back into the science and engineering laboratory. It's amazing that for decades they were on divergent paths, advances in science and engineering and manufacturing going further and further from each other. And 3D printing has brought it back together again. We can do it in the laboratory, scientists and engineers back making things, and we can customize. So we can design on the screen, or we can scan a three-dimensional object and replicate that object by 3D printing.
So tell us about bioprinting then.
Bioprinting. Right, so bioprinting is where we use all of the principles of 3D printing, but now we introduce living cells. Now that sounds easy, but it's been quite a journey. We've had to develop inks that sustain the cells in the ink reservoir, that keep them in suspension during the printing process. And then imagine this, we're going to squirt living cells through a print head where they endure and encounter quite incredible forces. And so we do that, we protect them by using materials that absorb that energy. These are important parts of the bioinks. They're so-called biopolymers that protect the cell during the printing process. And then, when they get to the other side of the printing head, we can create those 3D structures containing the cells, keeping the cells where we want them, and build very sophisticated structures with materials and living cells.
So that sounds very fancy, but tell me about the why behind bioprinting. Why is bioprinting, what does it do that, say, tissue engineering can't achieve?
Yeah, so tissue engineering has really provided a tremendous platform for 3D bioprinting. We've developed a whole inventory of materials, and we know how those materials behave as they interact with living cells. We understand the fundamental interactions, but with tissue engineering, we want to use that combination of the materials and the cells to regenerate damaged tissue. Now imagine biology, well don't imagine, it is. Biology is three-dimensional, right? So we need to be able to create three-dimensional structures that are ordered, take those materials from the inventory, print them out, put the cells where we want them in 3 dimensions in order to build up the very sophisticated structures. So this doesn't replace tissue engineering. It builds on the mountains of knowledge we've created in tissue engineering in order to create much more efficient structures.
So we started this project together, Gordon, a couple of years ago to try and address an issue called Microtia. Microtia is a congenital condition which causes a malformation of the ear. So patients are born with either with a hearing issue but also a cosmetic issue. And reconstruction at this stage is very problematic. It takes many stages. It's fraught with complications, not only to the donor side but of course to the graft side as well. So Gordon, how is bioprinting going to help provide a solution for this problem?
So as I've mentioned, we can create 3D structures by scanning a 3-dimensional object, and then we can replicate it. And so it's very easy to replicate the shape of an ear. We can take a handheld scanner and scan that ear, and we can transform that into a software package which can replicate the shape of the ear. That's not a problem. But the ear is sophisticated, as Payal knows. It's very amazing distribution of mechanical properties. If you feel your own ear, you'll see just how complex that structure is. And I did say feel your own ear. Don't feel anybody else's. And you'll see how complex that structure is. So we've been able to create a printer which creates a replica of this, not just in shape and mechanical properties, but prints a soft material into the interstitial volume of that mechanical structure. And that soft material we can use to regenerate the cartilage of the ear. And we've got all of that distribution of mechanical properties that we need. So at this point in time, we 3D print the ear with all of the distribution, with very clever internal structures, still facilitating cartilage regeneration. And we provide that ear to Payal and to her team for the transplantation into a patient with Microtia. Subsequent to that transplantation, the cells are in the right environment that we've printed in order to proliferate and differentiate into cartilage, a living ear.
Yeah, absolutely. And we're in this critical phase of our research right now that research now needs to come to a clinical site. So we're really grateful for the support from Teresa Anderson, our CEO, in helping us set up this first bioprinting laboratory in a New South Wales hospital that's located within the Institute of Academic Surgery and Transplant Institute.
So why is that so important to have that location on site?
Yeah, glad you asked. As you know, our scientists have been doing a lot of work on the scaffold preparation work of the research. So we've been able to get data, model the ear, and study the different biomechanical properties of the scaffold. But now we're at a stage where we're at the ink formulation part of the project. And that involves taking stem cells and getting them to mature towards cartilage. Now we know that stem cells are more likely to grow towards cartilage and stay towards cartilage if we co-culture them with mature chondrocytes. So for that we need tissue. And it just so happens that routine ENT surgery, such as septoplasty surgery, where we often fix the septum so people can breathe better, there is often excess redundant cartilage we end up discarding. And we've been very lucky in already attaining ethics approval and currently recruiting patients to be able to use that otherwise discarded cartilage as a source for chondrocytes to mature with our stem cells. So once we then get the work happening with the ink formulation, the next step is to put it into this customized bioprinter, which is a labor of love, I hear, where we can layer by layer print scaffold and stem cells, so we get a 3D printed ear. That ear is eventually implanted, and the idea is that scaffold absorbs away over time, but leaves the anatomical construct so the cartilage grows and matures in the shape that we want, thus growing into a living, breathing human ear with a touch of magic of science. So tell us a little bit about 3D Alec, Gordon.
So, as I introduced in the animation, it's a complex 3D printer which has been customized and built in our laboratories at Wollongong for this particular application. And 3D Alec is actually making his first public appearance on the stand, on the booth, if you want to have a look at it later on. But we've turned what was a vision in that animation into reality. We have created a printer that can create all of the components that are needed for the 3D printed ear. so as to provide that in your clinical environment for use with your patients. And having that printer in your environment, which it will be very soon, Payal, I'm sure will make a huge difference.
Yeah, I think the benefit of this for this project is, firstly, we want to work towards a one-stop shop. So the idea is, in the future, if a patient comes in, they have their stem cells and tissue harvested, that gets bioprinted and implanted, hopefully within the same admission. But having that bioprinter in a clinical location also then allows us to upscale. I mean, the ear, nose, throat anatomy is heavily reliant on cartilage, both for structure and function. So imagine if we crack the code for cartilage printing for the ear, imagine the implication for the nose. I mean, that's already a billion-dollar industry. And then imagine the application for the throat. There are so many patients, cancer patients, with poor speech and swallow issues, having lost their laryngeal framework. So I think that the potential is immense. But not only that, I'm a big believer that you bring basic science technology to a clinical site, that will then help cross-pollinate to other disciplines. I mean, we're working in collaboration with the Transplant Institute, so, you know, only the imagination is the limit here.
Yeah, and I can verify that that is certainly true. We've worked with a number of collaborators around the country to establish 3D bioprinting facilities for particular clinical applications in the clinical environment. And we're very fortunate in Australia because we do have a culture of collaboration. We know how to work together, we know how to bring different disciplines together, and we know the importance of doing that in the right setting to make sure we have effective translation. And of course, we've learned from amazing pioneers in this regard. We've worked for a number of years, a number of decades actually, with Professor Graham Clark of Bionic Ear Film. And amazing as Graham's feats were, technologically and medically, sometimes we forget the accomplishments in bringing together an interdisciplinary team more than 50 years ago in a very conservative university environment, and showing people the value of working together towards a particular clinical application. And it could not have been done. Even if all of the science and technology was right, it could not have been achieved without the assembly of the appropriate team. And Graham has introduced us to a range of clinical collaborators across the country. I don't have time to talk about all of the projects. Let me mention a couple. One is with another ENT surgeon in Wollongong, Stuart Mackay. And with Stuart, we're using 3D printing to print replicas of a patient's airway so that we can design, or Stuart can design, the most appropriate intervention for that patient to treat sleep apnea. We're also working with Professor Toby Coates at the Royal Adelaide Hospital, and Toby is involved in islet cell transplantations to treat diabetes. That's not a very effective procedure at the moment. So Toby's idea was, well, let's 3D print a structure wherein we protect the islet cell, we surround it with other cells that will ensure its viability and fight off the immune reaction and other growth factors. And we have designed and delivered to Toby a printer dedicated to that 3D printed islet cell structures. And then there's Professor Peter Chung, a relation to this project, because it was with Peter we started to develop the idea of printing cartilage, this time for the ear, for the knee, and I was printing into the knee, into a defect, this special ink that would help recreate cartilage. Now, this was an interesting project because it really illustrates, as our project does, that we have to have an interweaving of the development of the bioink and the cell interactions with the actual hardware, with 3D ALIC, for example, for the 3D printed ears. In Peter's case, it was a handheld pen that could print directly into the defect in the knee, and that's a much more efficient way to ensure cartilage regeneration. And of course, collaborations spur other collaborations. We're now involved in collaboration in the manufacturing sector, where we're looking at how we can mass produce that particular biopen for clinical application. And more locally here, another example, building on that biopen, as I say, collaboration spurs collaboration. Professor Gerard Sutton from the Sydney Eye Bank approached us to develop a pen that could print directly into the eye for corneal regeneration or to treat ulcers. And we've developed the iFix pen with Gerard. As you know, Gerard won the big idea last year was the iFix pen. And we've developed the hardware and the transparent ink to turn this into a reality.
Yep.
Another important point about collaborations is that we need them not just nationally, but globally. We need those collaborations if we want to ensure the maximum impact for the science and technology and the clinical protocols that we develop. Working with Jared, who works a lot in Myanmar, we've seen that there's a real need and application for the iFix pen in developing countries. And so we now have a parallel project that's looking at a different version of the iFix pen specifically for that use.
Yeah, and I think, you know, one of the things, even with our Microtia project, is often the incidence of a disease. You know, we may be leading the globe in developing a technology, but the incidence of the disease is not the highest here. So whilst we're developing it, we need to keep an eye on the bigger picture and focus on global translation. It's interesting you discussed cochlear implantation earlier. So let's talk about cochlear implants. In Australia, it's an Australian innovation. In Australia, a patient who needs a cochlear implant gets the best cochlear implant. Any child who is born congenitally deaf is screened at birth. It's mandatory newborn hearing screening, and gets fast-tracked to the technology that allows them to develop, go to normal school and develop as a normal individual otherwise. However, in other parts of the world, such as in India, where I went on a cochlear implant conference last year, if you can't afford the technology, which costs $25,000, you don't get it. So that then leads to inequity and injustice in distribution of healthcare. So such as I became aware that little kids born there, sometimes the parents were affording the technology for the male children rather than female children. So because there was this perception that the boy is going to grow up and earn the family a living, whereas the girl is not going to do the same. So you have this generation of young girls who are growing up whose real future is to make a marriage of some sort and be a vessel to bear children and do housework, because they're never going to learn to hear or speak. And that's really sad. And I think as global leaders, if we are then working on a technology, we really owe it to ourselves to think about the bigger picture, to think about the translation on a global front. So when I came back from India last year, we really sort of started approaching some colleagues and doing some work looking at Microtia. And we've already learned so much in that journey. For example, to understand the lack of technological infrastructure, basic science infrastructure there, to understand their economic infrastructure that helps research, and for them to understand the technology, to start working with it. It means that if we're putting those building blocks in now, in 5 years' time, when we're ready for clinical trials of our bioprinting project, we've got a global clinical trial happening, not just one in Australia. Is that what you found in your global projects otherwise?
Yes, and I think it is important to remember that it's the complete package that we need to deliver. Having identified what is a global need and a global opportunity to deliver Australian science and technology and clinical protocols, we must deliver that complete package. And of course, part of that is the people that need to be trained in those areas. And again, Australia is at the forefront of this. We were fortunate to get into 3D bioprinting at a very early stage. We have master's courses in 3D bioprinting at QUT and University of Wollongong in collaboration with our European partners. We have online courses, either short courses or a fully online master's course. So you can see we can not only deliver the protocols and the hardware and the ink, but we can actually deliver the training globally.
And I think the important reason to do that, to attack it from all ends, is so we're translating in 5 years, not 25 years.
That's right. It really is an exciting time to be a researcher. These are some of the researchers in our laboratory, as you can see. You must come and visit us if you're ever down in Wollongong. I can introduce you to some very amazing people who are totally committed to projects like we've just been talking to you about. This younger generation of researchers not only is at the forefront scientifically and technologically, but they're at the forefront of understanding how to translate our fundamental discoveries into real applications as quickly as possible. We really have put the ability to create back in the hands of creative. That nexus that I spoke about before, that divergence of science and engineering and clinical practice from manufacturing has been reconnected. It's exciting times.
Yeah, and I think as an academic, what I'm finding very interesting is that, as you say, our research collaborates are not just limited to our scientific links. It's where now this technology is making us interact with government, with industry, with regulatory bodies, with hospitals. And as the Deputy Chair of the State Committee of the College of Surgeons, I'm really looking forward to having both you and Teresa as our panelists next week when we have this event with the TGA and the ACI to discuss the regulatory issues in more detail.
Yeah, as you can imagine, the regulatory issues in this area are quite complex. This really is a personalised medicine. It's my personalised water bottle, so I'll just be a second.
But I suppose you're about to say that as Australia, we're leading in that front as well. Is that fair to say?
Yeah, that was my line. So it is great that we're working along with the regulatory bodies, side by side, hand in hand, in order to confront these quite complex issues from a regulatory point of view. Because there was a fear just a few years ago that it might be the non-technical issues that become the stumbling block in implementing and translating this science and technology. So we have the collaboration on the science, the technology, the training, the medical front, and now working with the regulatory front. It's an exciting package.
Yeah. So I think we're going to wander over there and have a look at what this smart little desktop printer has printed for us. And essentially what we can see is that whilst we've been talking, this little printer's printed a little replica model of an ear. And it is really that simple and it's that fast. So if we can do this for ear today, imagine the possibilities of what we can do tomorrow. The theme today is Imagine, Transform, Lead. Well, I can tell you that RPA is leading the state in championing this technology. So I'm really looking forward to having each and every one of you join us and celebrate at our lab launch next month. And of course, if you wanted to come and meet Trudy Alec or have a conversation with any of our scientists about the technology, you're most welcome to come join us at our booth just next doors. Thanks so much.
Thank you.